The story behind the famous Spitfire Mk.IX fighter began with two Spitfire Mk.V airframes. They were handed over to Rolls-Royce specifically to test out the powerful new Merlin 60 series engines. Testing at the factory airfield showed absolutely outstanding results. It turned out the aircraft could easily be upgraded to take the new power plant. This was done without any major changes to the basic airframe. This required minimal modifications. It meant they could push it into mass production incredibly fast. At the same time, the leap in flight performance was massive, and that is no surprise. At an altitude of around 33,000 feet, the power output of the new Merlin engine practically doubled. Compared to the older Mark V, the top speed of the new fighter jumped by roughly 70 miles per hour. Its service ceiling increased by almost 10,000 feet. To test the new setup in action, they ran a series of mock dogfights at a British airbase. The adversary was a captured German Focke-Wulf 190A fighter. The results of these mock battles put any remaining doubts to rest. The new Spitfire variant showed total speed superiority at medium and high altitudes. On top of that, the British fighter boasted a much higher climb rate. This was true even down at lower altitudes. And that is exactly how the legendary Spitfire Mk.IX was born. Interestingly enough, it was originally seen as nothing more than a temporary stopgap. The designers only planned to produce this variant until full-scale production kicked off for the next major version. This was the Spitfire Mk.VIII. Fitting the new engine required a reinforced airframe and a slightly reshaped cowling. The old 3-blade propeller was swapped out for a more modern 4-blade design. Because the new power plant was bulkier, the fuselage of the Mk.IX ended up being slightly longer than its predecessor. After getting the green light from the Air Ministry, factories rushed to upgrade the engines on the fighters. They decided to kick off the process by converting fresh Spitfire Mk.V airframes. These came from the latest production batches that had not even left the factory floor yet. The first large-scale upgrade program started in June 1942. By the end of the month, the RAF had already received its first 18 updated aircraft. Production rates steadily climbed. They rolled out 38 fighters in August. By October, that number hit 58. Toward the end of 1942, British factories began building completely new Spitfire Mk.IXs from scratch. By the summer of 1943, the variant was in full mass production across several major assembly lines. The fighters from that very first batch were sent straight to the front lines. They were assigned to No. 64 Squadron. They saw their first combat action on July 30th. Just off the French coast, a flight of the new Spitfires tangled with about 15 German Focke-Wulf 190A fighters. The results were spectacular. 3 enemy fighters were shot down into the channel. Meanwhile, the British pilots returned to base without a single loss. Throughout August, 3 more units completely transitioned to the new fighters. These were No. 611, 401, and 402 squadrons. By August 19th, these aircraft were heavily involved in providing air cover for the massive amphibious landing at Dieppe. The combat debut of the new Spitfire Mk.IX proved to be incredibly successful. Their victory tallies, especially against German fighters, started climbing rapidly. It's an interesting paradox. The Spitfire Mk.IX was originally designed just to be a temporary stopgap while they waited for future models. However, it ended up outlasting all of them. It remained in production right up until the very end of the war. Naturally, the aircraft's design was continuously improved as time went on. As mentioned earlier, the whole program started off as a simple conversion of older airframes. These early aircraft looked exactly like their predecessors. The only major change was the new engine. In those early stages, even the armament remained the same and did not see any major upgrades. Eventually, purpose-built Spitfire Mk.IXs began rolling off the assembly lines. They came in 3 specialized variants tuned for medium, low, and high altitudes. The standard medium altitude version initially featured the Merlin 61. It later received the even more powerful Merlin 63 and 63A engines. The wings on these fighters could be standard or clipped. This improved roll rate and low-altitude maneuverability. The low-altitude variants entered production in early 1943. They were powered by the 1,580 horsepower Merlin 66. The vast majority of these aircraft featured clipped wings, though if needed, the wingtips could be easily swapped out right in the field. Meanwhile, the high-altitude variant was powered by the Merlin 70. It was fitted exclusively with standard span wings. All three variants were constantly updated. They borrowed the best engineering solutions from the parallel Spitfire Mk.IX program. Over time, designers installed a new broad-chord pointed rudder and added an improved air intake filter. They also fitted an extra fuel tank holding about 86 gallons right behind the pilot. The cockpit was equipped with an innovative gyro gun sight. This drastically improved gunnery accuracy. The aircraft received a new reinforced wing, allowing for a heavier armament loadout. This included two 20mm cannons and two 50 caliber machine guns, along with underwing bomb racks. On top of that, the tailwheel was finally made fully retractable. Toward the end of the production run, factories started rolling out fighters with a cut-down rear fuselage and a teardrop canopy. This gave the pilot excellent 360-degree visibility. However, because of this design change, the rear fuel tank capacity had to be slightly reduced. It now held about 79 gallons. Initially, priority for delivering the new Mk.IX went to home defense squadrons. These operated under the air defense of Great Britain. But as the Allies geared up for the invasion of northern France, the main focus shifted. They started transferring the aircraft in large numbers to tactical Air Force units. These units were tasked with supporting operations on the European continent. Following the successful Allied landings in Normandy, the Mk.IX formed the backbone of the Royal Air Force's frontline fighter force. Their role was incredibly versatile. They operated as traditional fighters. They provided air cover for ground troops and patrolled the skies over airfields and transport hubs. They also intercepted enemy bombers and reconnaissance planes. At the same time, they were heavily used as fighter bombers for ground attack missions. These aircraft escorted heavy bombers during daytime raids. They also actively hunted down the German V-1 flying bombs used by the Third Reich to terrorize British cities. Spitfire Mk.IXs fought their way through France, Belgium, the Netherlands, and Germany right up until the final surrender. They also saw heavy action on the Italian front. On October 5, 1944, a pilot at the controls of a Spitfire Mk.IX scored a historic victory. He achieved the first confirmed kill of the cutting-edge German Me-262 jet fighter. On that day, 12 Canadian pilots were flying a combat patrol over the Nijmegen area in the Netherlands. The German jet was flying at low altitude. This was a fatal mistake the Canadians instantly capitalized on. Building up tremendous speed in a steep dive, they caught the fast German fighter and shot it down with accurate fire. Later that year, on December 29th, another spectacular dogfight unfolded. Flight Lieutenant Richard Odette, flying that same Spitfire Mk.IX, pulled off the unbelievable. In a single sortie, he single-handedly shot down 3 German FW-190s and 2 Bf-109s. He destroyed more enemy aircraft than the rest of his unit combined, who only managed to tally 3 kills between them. Toward the end of the war, the legendary Spitfire Mk.IX was heavily used for ground attack missions. Though, of course, the pilots never passed up a chance to shoot down any enemy aircraft that had the misfortune of crossing their path. To make the fighter even more effective in the ground attack role, engineers ran a whole series of experiments with rocket armament. For example, they tried mounting American M10 rocket pods under each wing. These were 3-tube, 4.5-inch launchers. They were essentially an airborne version of the infantry bazooka. They also tested British triple-tube 3-inch rocket launchers. They also tested standard 4 rocket setups mounted on special zero-length launchers instead of the older massive rails. However, all these interesting rocket projects never made it past the experimental stage. Meanwhile, the rapid Allied advance meant the Spitfires needed longer legs to cover much greater distances. During testing, they hung a variety of drop tanks on the Mk.IX. These included American teardrop tanks under the wings. They also tested huge cigar-shaped centerline tanks that held over 238 gallons of fuel. In the end, though, the designers went with much more practical 60-gallon streamlined tanks. They turned out to be the best option. They completely replaced the older flush-mounted slipper tanks that used to sit under the center section of the wing. It is worth noting that it was not just the British flying the Spitfire Mk.IX into combat. Many pilots from other nations flew them as well. First and foremost, these were airmen from foreign national squadrons fighting within the Royal Air Force. To give you an idea of the scale, these aircraft equipped 9 Polish squadrons, 7 French, and 3 Czechoslovak squadrons, as well as 2 Belgian, 2 Norwegian, and 2 Greek squadrons. Plus, 1 Dutch squadron flew them. These fighters were also heavily used by special mixed squadrons. While they officially belonged to the British military, they were completely made up of volunteers from all over the world. Beyond the foreign squadrons integrated into the RAF, the Spitfire Mk.IX was also supplied directly to other Allied powers. Starting in early 1944, the aircraft began arriving in the Soviet Union. In total, nearly 1,200 of these fighters were delivered. The vast majority were the LF Mk.IX variant, alongside a small number of LF-16s powered by American-built Packard Merlin engines. Despite being capable aircraft, Soviet testing revealed that the Spitfire's optimal combat environment was much higher than the typical low to medium altitude dogfights of the Eastern Front. In that lower airspace, specialized Soviet fighters like the La-7 often possessed an edge in raw speed. Consequently, Soviet command largely refrained from deploying the Spitfire in frontline tactical roles. Instead, these aircraft were primarily assigned to rear echelon air defense regiments. They successfully protected strategic airspace over cities like Moscow, Leningrad, and Murmansk, serving as highly capable high-altitude interceptors where their superior service ceiling allowed them to engage high-flying German reconnaissance planes that were out of reach for standard Soviet fighters. Following the end of the war, the Spitfire Mk.IX remained in Soviet service for several years. Thanks to its excellent handling characteristics, forgiving nature, and high-altitude capabilities, local aviation workshops converted a number of them into two-seat trainers. The Spitfire played a key role as an advanced trainer, helping pilots master high-altitude flight before transitioning to the first generation of jet aircraft. Beyond the mass-produced tactical variants, there were also a few highly specialized versions of this aircraft. One of the most interesting was the high-altitude interceptor. They had to be rushed into service because new German high-altitude reconnaissance aircraft and bombers, the Junkers 86P, suddenly appeared in the skies over England. They were followed a bit later by the even more advanced Junkers 86AER. Earlier models, like the Spitfire Mk.IX, were completely helpless against them. Their engines simply could not produce enough power at those extreme altitudes. The solution was to quickly upgrade a few Spitfire Mk.IX fighters. Their engines delivered significantly better performance. For instance, the new Mk.IX could reach the maximum altitude of the Mk.VI, which was 43,600 feet, a full 10 minutes faster. Because of this, in early September 1942, a dedicated flight of high-altitude interceptors was formed at an RAF base. Interestingly, these were not the production, high-altitude HF Mk.IX versions which came along much later. At the time, the pilots received the standard F Mk.IX variant with Merlin 61 engines. However, they were fitted with modified reduction gearing and lightweight propellers. To make the aircraft as light as possible, ground crews ruthlessly stripped out unnecessary equipment. They removed all the heavy armor and even the machine guns, retaining only the cannons. They also gave these fighters a highly unusual paint scheme. Instead of the traditional camouflage, they were painted a solid gray-blue, just like photo reconnaissance aircraft. The gamble paid off. On September 12th, one of these lightened Spitfires successfully intercepted a German Junkers at a staggering altitude of 44,300 feet. The enemy pilot tried to escape by climbing even higher. However, the British fighter relentlessly pursued him all the way up to 47,200 feet. There, a well-aimed cannon burst seriously damaged the wing of the German aircraft. In 1944, a number of Spitfire Mk.IXs were converted into high-speed, short-range reconnaissance planes designated the FR Mk.IX. What really set them apart from standard combat fighters was a specialized camera. It was mounted in the fuselage right behind the cockpit, with the lens pointing to the left. This allowed the pilot to capture high-resolution photos of enemy positions. Meanwhile, the standard armament was fully retained, so the aircraft could still easily defend itself in combat. Between 1944 and 1945, these speedy FR Mk.IX reconnaissance fighters proved highly successful, flying over the front lines in France, Italy, and Germany. If you tally up the total number of Spitfire Mk.IXs and their related variants ever built, production easily surpassed the records set by the earlier Mk.V. That being said, with the end of the war rapidly approaching, many of these newly built aircraft never actually made it to the front lines. Instead, a completely new breed of even more lethal and advanced Spitfire variants entered service. On these new fighters, the tried-and-true Merlin engines made way for absolute engineering monsters. These were the massive, far more powerful Rolls-Royce Griffon power plants. The legendary Spitfire is an all-metal, low-wing monoplane. The wing consists of 3 main sections. These are a center section that is structurally integrated into the fuselage, and 2 detachable outer wing panels. Viewed in plan form, the wing features that beautiful, iconic elliptical shape with a very thin airfoil. The internal structure is built around 2 main longitudinal spars. The front spar is substantially thicker than the rear one as it absorbs almost all the flight loads. To prevent the wing from twisting under extreme aerodynamic stress, the leading edge is reinforced with a thick, heavy gauge skin. The rear spar helps maintain the wing's rigidity, and it serves as the mounting point for the freeze-type ailerons. On earlier production variants, these movable control surfaces were actually fabric-covered. Underneath the wing, you will find Schrank-type split flaps. Due to the unique curvature of the wing's underside, engineers had to divide these flaps into inner and outer sections. These were then pneumatically operated. The wing's internal framework was incredibly rigid. At the same time, the outer metal skin was kept perfectly smooth using flush rivets. The wingtips actually came in 3 different styles. These were the standard rounded tips, clipped ones that looked almost rectangular, and extended, pointed versions. Interestingly, fighters shipped with clipped wings often came with a spare set of standard tips. This allowed mechanics to easily swap them out in the field if needed. The aircraft's fuselage used a semi-monocoque design. This means it had a rigid internal skeleton made of metal frames and stringers. It was all wrapped in a metal skin that also carried a significant portion of the structural load during flight. In cross-section, the fuselage was shaped like an ellipse. The nose section was assembled using flush rivets to keep the aerodynamics as clean as possible. Meanwhile, the tail section used standard dome head rivets, and of course, the cowling panels covering the engine were completely removable. This made maintenance and repairs much easier. The internal layout of the Spitfire was typical for single-engine fighters of the era. You had a powerful engine up front. Right behind it, separated by a firewall, were 2 fuel tanks. Just behind those, past another fireproof bulkhead, was the cockpit. It was enclosed by a clear plexiglass canopy that slid back on a set of rails. The standout feature of this canopy was its signature bulge design. The sides bulged out past the fuselage by about 3.1 inches. This gave the pilot an excellent field of view to the rear and sides. This was absolutely critical in a dogfight. On top of that, the pilot could check his 6 using a rear-view mirror mounted right above his head. The windscreen was made of flat panels that did not distort the view at all. The center section was built from heavy-duty armored glass. To make getting in easier, they included a small drop-down door on the left side of the fuselage. In an emergency, the canopy could be completely jettisoned rather than just slid back. To bail out, the pilot had to yank a release handle and push the canopy up just a bit. This let the powerful slipstream rip it away. In practice, though, the release cable would sometimes snap. The pilot would be left holding the handle with the canopy jammed in place. For those nightmare scenarios, there was a small crowbar stowed on the inside of the left-hand door. You were supposed to use it to smash your way out, assuming you had the time, of course. Inside, the pilot sat on a composite plastic seat. It was mounted relatively high off the floor of the deep cockpit. The seat itself was made of 4 separate pieces held together by metal brackets. An Irvin parachute fit right into the seat bucket. The pilot could easily adjust the seat height using a handle on the right side. The flight harness featured a clever spring-loaded system. The pilot could release the tension to lean forward toward the instrument panel. It would then automatically retract and lock tight again. Behind the pilot was an armored backrest and headrest. That being said, this steel plate was only 0.2 inches thick. German 7.92 millimeter armor-piercing rounds could easily punch right through it. The aircraft was flown using a long control stick with an articulated top section. It also featured standard rudder pedals. British engineers designed these pedals with 2 different height levels. During normal cruise, the pilot's feet rested on the lower rungs. But when a fierce dogfight broke out, he needed extra leverage for aggressive maneuvers, so he would shift his feet up to the top level. Right behind the seat was a heavily reinforced fuselage frame. It essentially acted as a roll bar. This protected the pilot if the aircraft flipped over during a crash landing. The instrument panel in the cockpit was a two-piece design. It had really well thought-out ergonomics. The main panel was made from a durable phenolic composite. This was nearly a quarter-inch thick. This is where engineers placed the primary engine gauges and auxiliary controls. The flight and navigation instruments, however, were mounted on a separate aluminum panel. To protect those sensitive gauges from flight vibrations, this center panel was suspended on spring-loaded shock mounts. The compass was completely separate. It sat on its own bracket just below the main panel. Here is an interesting detail. Standard cabin heating simply did not exist in the Spitfire. The designers only provided a plug for an electrically heated flight suit. Pilots had to wear special gloves and boot insoles wired with heating elements. In practice, though, this setup was notoriously unreliable. Pilots rarely used it and ended up freezing more often than not. As for ventilation, fresh air flowed into the cockpit through a small vent. This vent was located on the right side of the fuselage just ahead of the windscreen. The pilot could control the airflow by simply turning a knob. Right behind the pilot sat a rear fuel tank. It was placed along with a variety of electrical and radio equipment. Ground crews could easily reach it through an access panel on the left side. Interestingly, almost the entire rear fuselage was left completely empty. The new engines were a lot heavier than earlier variants. Because of this, engineers had to adjust the center of gravity. To do this, they moved the heavy battery and the oxygen cylinder all the way back into the tail section. The construction of the tail section was pretty sophisticated. The main fuselage blended smoothly into a detachable tail section. This section was built as a single unit with the vertical stabilizer. Its structural frame and outer skin were made from lightweight, aircraft-grade aluminum alloys. The horizontal stabilizer had a sleek, elliptical shape. It was made up of two halves. They locked together securely inside the fuselage. They ran perfectly parallel to the center line of the airplane. All the airfoils on the tail were perfectly symmetrical. The control surfaces also had a metal frame. But unlike the rest of the fuselage, they were covered in aircraft fabric and sealed with dope. The design was constantly being tweaked. Early models featured a rounded top on the rudder. Later, it was made significantly wider with a pointed tip. Later versions of the Spitfire Mk.IX were also fitted with enlarged control surfaces. This allowed for even better maneuverability in combat. The heart of the Spitfire. Mk.IX was one of several variations of the famous British Rolls-Royce Merlin 60 series engine. This was an incredibly powerful liquid-cooled V12 engine. It had a displacement of 27 liters. The engine was solidly mounted on a tubular engine mount. Here, engineers combined welded, riveted, and bolted joints for maximum resistance to G-loads. Most often, you would find a Merlin 61, 63, 66, or 70 under the cowling. Each was tuned for peak performance at a specific altitude. The 61 and 63 models used traditional carburetors. Meanwhile, the 66 and 70 versions were fitted with advanced American Bendix-Stromberg pressure carburetors. These could automatically adjust the fuel mixture depending on the altitude. This feature took a lot of the workload off the pilot. All these engines were equipped with two-stage superchargers. The first stage ran continuously. The second stage automatically kicked in as the fighter climbed to higher altitudes. The cooling system for this beast ran on a pressurized water glycol mixture. This fluid circulated through the intercoolers. It cooled the fuel-air mixture before it reached the cylinders. The expansion tank was mounted directly onto the engine reduction gear casing. At the same time, the designers cleverly housed the radiators inside two symmetrical fairings under the wings. The right wing housed the first half of the main radiator and the oil cooler. Meanwhile, the left wing held the intercooler and the second half of the main radiator. Airflow was fully automated and managed by thermostatically controlled radiator flaps. Here's an interesting detail. The automation was designed to completely lock out the second stage of the supercharger. This happened if the coolant temperature approached the critical 115 degrees Celsius mark. Carburetor air was drawn through a scoop under the center section of the wing. To prevent dust ingestion during takeoff, the pilot could close a flap. This drew cleaner air directly from inside the engine cowling. On later production blocks, an upgraded heavy-duty filter was added. This required a noticeably extended forward-facing air intake. Another brilliant engineering detail was the exhaust system. Each engine cylinder had its own individual exhaust stack. These were swept back at an angle to generate actual jet thrust. This clever ejector exhaust design provided a nice, free boost to the aircraft's top speed in flight. Fighters powered by the famous 60 series Merlin engines were fitted with reliable 4-blade Rottle propellers. Depending on the variant, the blades were made of either forged duralumin or a special wood composite. This composite was impregnated with bakelite resin for extra durability. Later engine variants like the 63, 66, and 70 were also paired with these wooden props. All of these featured a constant speed, automatic pitch control system. This significantly reduced the pilot's workload during a dogfight. The heart of these fighters, the 60 series engine, demanded high-grade 100-octane avgas. But when these aircraft were shipped to the Soviet Union under Lend-Lease, the fuel situation got a bit complicated. Soviet crews either had to rely on scarce imported fuel or run the planes on a domestic leaded gas designated 4B70. Fortunately, the rugged British engine didn't suffer from detonation on this local fuel. However, it couldn't quite produce its maximum power output. The fighter's fuel system was incredibly well thought out. It consisted of 3 internal fuselage tanks. 2 were placed right in front of the cockpit, securely protected by a firewall. The bottom tank was considered the main one. It held about 44 gallons of fuel. It featured a self-sealing coating to protect against punctures and fed directly to the engine. Sitting right above it was a 58-gallon upper tank. It wasn't self-sealing but worked on a clever principle. Pressurized gas simply forced the fuel down into the main tank. Both tanks were capped by a 4mm thick steel armor plate. Some variants had a third 35-gallon tank installed right behind the pilot's seat. However, it was rarely used and usually only in combination with a large external drop tank. This was because completely filling that rear tank severely shifted the aircraft's center of gravity in flight. To extend its range, the fighter could be fitted with 4 different types of external drop tanks. 3 of them were conformal slipper tanks with capacities of 30, 45, and 90 imperial gallons. They had a distinct shape that fit flush against the underside of the fuselage. They also featured a special built-in channel to accommodate the carburetor air intake. Their release mechanism was incredibly well thought out. When jettisoned, the tank would first slide smoothly backward along guide rails before dropping clear. This ensured it didn't strike the aircraft. The 4th option was a 50-gallon cigar-shaped drop tank. This mounted to the exact same racks used for carrying bombs. There was one important catch, though. The pilot could only start drawing fuel from these external tanks once the aircraft had climbed above 2,000 feet. As for engine oil, the aircraft didn't use a conventional separate oil tank. Instead, that role was filled by a tank that actually formed the lower section of the engine cowling itself. It held about 6.5 gallons of oil. It was also securely fastened to the engine mount with specialized clamps. The landing gear design on the legendary Spitfire was famously unusual for its time. Instead of retracting inward toward the fuselage, the main gear did the exact opposite. It folded outward toward the wingtips. This engineering choice allowed the wing to remain as thin and aerodynamic as possible. However, it also meant the track width between the wheels was quite narrow. This made the fighter notoriously tricky to handle during touchdown and taxiing on rough, unpaved airstrips. A hydraulic system operated the main landing gear. If the engine-driven pump failed in combat, the pilot had a reliable backup plan. He could blow the gear down using compressed carbon dioxide from an emergency bottle located right inside the cockpit. To soften the impact of landing, the main gear utilized reliable Vickers oleo struts. The wheels themselves measured roughly 24 by 7 inches. They sat at a slight outward angle and were equipped with powerful Dunlop pneumatic brakes. In flight, the gear tucked neatly into wheel wells inside the wing. The strut and the outer half of the wheel were covered by aerodynamic fairings. The tail wheel was fully cast-ring, meaning it could swivel 360 degrees. It also featured its own oleo shock absorber. Interestingly, on early production runs of the Mk.IX, this tail wheel was fixed in place. It was not until later modifications that engineers made it fully retractable. It folded back into the fuselage where it was concealed by flush doors. A pneumatic system powered by an engine-driven compressor operated practically everything else. This system controlled the retractable landing light, wheel brakes, radiator flaps, and gun firing mechanisms. It even shifted the supercharger speeds. All the compressed air needed for this was stored in twin air bottles. These were located on the port side, just aft of the cockpit. To power the aircraft's electrical systems, it was equipped with a 500-watt generator and a reliable battery housed in the tail section. Electrical power was critical for the landing light beneath the cockpit floor, navigation lights, and the radio. It also powered the instrument panel lighting, the reflector gun sight, and various warning indicators. Interestingly, even though the engine featured an electric starter, ground crews usually started it using a heavy external power cart. They would wheel it over and plug it directly into a receptacle under the wing root. However, if a combat scramble demanded an immediate engine start at an austere forward airfield, pilots could use a Kaufman pyrotechnic starter. The entire onboard electrical network ran on a standard 12-volt system. The famous Mk.IX was also perfectly set up for harsh weather conditions. It featured an anti-icing system that sprayed the cockpit windshield with a mix of distilled water and ethylene glycol. A small spray nozzle was integrated right into the base of the windshield frame. To clear the view, the pilot simply used a manual pump located on the right side of the cockpit. When climbing to high altitudes, the pilot had to wear an oxygen mask. The main oxygen cylinder was securely mounted in the tail of the aircraft. British engineers designed a very smart setup. Instead of a continuous flow, a demand valve delivered oxygen only when the pilot inhaled. This significantly conserved the air supply during the flight. Communication in combat is critical, so the fighter was equipped with the most advanced radio available at the time. The latest versions were tied into radio navigation gear, acting as an early blind landing system for low visibility conditions. To make it easier for mechanics to swap or fix the radio, it was mounted on a slide-out tray. On top of that, British aircraft were required to carry an IFF, or Identification Friend or Foe system. This gear was so highly classified that it had a built-in explosive charge for self-destruction. If a pilot had to make a forced landing in enemy territory, they were supposed to detonate the unit immediately so the technology wouldn't fall into the wrong hands. The main radio antenna ran from the mast just behind the cockpit to the tip of the vertical stabilizer. The separate IFF antennas were strung from the fuselage to the tail section. Tucked just behind the pilot was another interesting feature, a slanted launch tube that housed a parachute flare. Its main job was to help the pilot land safely on an unlit airfield at night. Deploying it was as simple as pulling a release cable. A hatch would open and the flare would drop out under its own weight. As for protection, the armor on the Mk.IX was relatively light. The main defense came from steel plates about 4 to 5 millimeters thick. These covered the most vulnerable spots, the pilot's back, head, and knees, as well as the upper fuel tank. The cockpit windshield was made of armored glass an 1.5 inches thick, which could save the pilot from direct hits. On the sides and bottom, the fuel tanks and ammo bays were shielded only by light duralumin plates, roughly 1/8 inch thick. The fighter's armament depended on the wing configuration and could vary. In one of the most common setups, the fighter carried 2 powerful British 20mm Hispano cannons in the wings, with 120 rounds per gun. Backing those up were 4 rapid-fire .303 caliber Browning machine guns, holding 350 rounds each. The cannons were mounted closer to the fuselage, right behind the landing gear bays. Their long barrels stuck out noticeably and were covered by aerodynamic fairings. Because the bulky feed mechanisms couldn't fit inside the thin wing profile, engineers had to add those characteristic teardrop-shaped blisters to the top of the wings. The machine guns were positioned a bit further out from the center, cleverly integrated into the wing's sturdy structure. To fit the bulky ammo boxes, the guns had to be staggered lengthwise by about 6 inches. Mechanics serviced them through hinged access panels on the underside. To keep the weapons from overheating in a prolonged dogfight, cooling jackets were fitted over the barrels. There was also a neat operational detail. Before every sortie, the gun ports on the leading edge were taped over with little square fabric patches. This was done to keep dust and dirt out of the barrels during the takeoff roll, and it also helped slightly reduce drag. The second the pilot squeezed the trigger, the very first rounds instantly tore right through that fabric barrier. Ammunition was fed from the boxes using a disintegrating metal link belt. The spent casings and links simply dropped out through ejection chutes in the bottom of the wing. Sometimes the fighter's armament was modified. Instead of the usual machine guns, it could be fitted with 2 additional cannons. In this rare configuration, the ammo capacity was 145 rounds for the inboard cannons and 135 for the outboard ones. On top of that, under the fuselage, the Spitfire Mk.IX could carry a single 500-pound bomb. An even heavier punch came with the reinforced E-type wing. Each of these wings housed a single cannon with 120 rounds. It was paired with a 50 caliber machine gun packing 250 rounds. On this Mk.IX model, engineers also added underwing bomb racks. This pushed the maximum bomb load up to an impressive 1,000 pounds. A typical combat loadout consisted of one 500-pound bomb under the fuselage and two 250-pound bombs under the wings. Pilots could drop a wide variety of British and American ordnance. This included high-explosive, fragmentation, incendiary, semi-armor-piercing, and even smoke bombs. The Spitfire Mk.IX variant also finally introduced rocket armament. This consisted of a pair of 3-inch unguided rockets. Depending on the warhead type, these rockets carried either 25 or 60-pound heads. In any of these configurations, the fighter could carry 2 rockets and a single 500-pound bomb into combat. To stop the guns from freezing and jamming at high altitudes, the gun bays were heated in flight. This was done using warm air bled from the radiators. On models with the C-type wing, they even routed hot air from the engine exhaust for extra heating. Fire control on the Spitfires was handled by a reliable electro-pneumatic system. On the early variants, pilots aimed through a standard reflector gun sight. Later aircraft were fitted with a more modern gyroscopic gun sight. This innovation made air combat a whole lot easier. Pilots could set their firing range in advance. They could also dial in the known wingspan of the target aircraft to score hits with much greater accuracy. To record the results of their shooting, a gun camera was mounted right in the left wing root. It could be wired to trigger automatically whenever the guns were fired. Alternatively, the pilot could run it manually just to film the dogfight. The fighter's onboard equipment also included a 6-tube flare dispenser. This fired different colored signal flares. These were launched at the push of a button using an electrical switch. Beyond just firepower, the designers also factored in pilot survivability. In the event of a forced landing in extreme conditions, the aircraft always carried a supply of drinking water and sealed emergency rations. It even included a compact inflatable life raft complete with a CO2 cylinder.